Hey everyone, today we're going to be talking about chemical equilibrium. First concept to discuss in chemical equilibrium is, of course, that we've always been really stuck on this idea, or well, at least up until now, we've been stuck on this idea that if a reaction arrow points from left to right, then that's the only direction that that reaction can go. Well, technically, yeah, we read from left to right, so that's going to be normal for us. But a good point to be made is what you can see down here in the bottom. And that is that not only can a reaction go forward, but a reaction can go backwards. Not every reaction, but a lot of reactions can occur in what we call a reversible reaction. What that ultimately means is, as you're going to see as I highlight this, right here I have my HGO. Right here I have my HGO. So that's mercury 2 oxide. Mercury 2 oxide in the first reaction is a reactant. Okay? In the second reaction, in the second reaction, it is a product. Well, if you look at it, in the first reaction, we're seeing a reactant that is breaking down into its two products. Okay? In the second reaction, we see two reactants adding together to form the one product. Well, if you really look at this closely, they're the same reactions basically. First one is decomposition of HGO into mercury and oxygen. Second one is the synthesis of HGO from mercury and oxygen. So these reactions, as long as everything is right in the world, can occur in both directions. So I keep saying this word equilibrium. What does that really mean in chemistry? In order to be at equilibrium, a reaction needs to basically be at, or it needs to be reversible. And what we mean is that the rate of the forward reaction is equal to the rate of the reverse reaction. So we were talking about rate of reaction. That, of course, means how fast the reaction is occurring. So if the reaction is occurring forward and backward at the same speed, then that means that the reaction is at equilibrium. So what that really equates to down here is that one HGO may turn into these, or I guess in this case to be aligned with the balance equation, two mercury oxides break down into mercury and oxygen, and then immediately two mercuries and an oxygen are going to combine again back into mercury oxide. That's what we are indicating here with this arrow pointing in both directions. We're saying that the product and reactant concentrations are going to stay the same when the reaction reaches that equilibrium. For those of you that like to see it visually, of course, this is what we're basically saying, that over time, the reaction rate of the forward reaction and the reaction rate of the reverse reaction are going to, at some point, equal each other. And you would have just a little bit of the reactants forming products, and then those same reactants products form back into reactants, etc. So you're going to see that kind of flip-flop. Now, you know how things go in chemistry. We always try to make it as complicated as possible. In order to do so, we have included what we call an equilibrium constant, and that is K with a subscript of EQ. It basically, what it does is it measures to what extent the reactants or the products are being converted into one another. Okay? And it's specifically talking about the forward reaction. And so when we look at this, if KEQ ultimately ends up being greater than 1, the reaction is favoring the products. And so what that means is that it is shifting from reactants to the products. So we would be getting more and more of the products. If KEQ were less than 1, then we would actually have the products breaking down more into the reactants. So we would see it kind of shifting back. We would have more of the reactants, and we wouldn't actually be getting the amount of product we really expect. If KEQ was equal, then that means that the amount of moles of the reactants would be equal to products. So we would have equal on both sides. Okay. Now, what do I expect you to remember from this? What I expect you to remember is that there is an equilibrium constant called KEQ, and depending on whether it's greater than, less than, or equal to 1 determines whether the reaction is shifting in one direction or the other. Okay, you will be told that KEQ, what KEQ for a reaction is, and you will likely be told or reminded that that means that it's shifting in one direction or the other. Okay, from there, your understanding would be to elaborate on that and say, okay, well, if it's shifting towards the products, then that means that I'm going to be creating more of the products, and ultimately it could shift back in the opposite direction once I do. Okay, so that's what we're going to be seeing with some demos on Monday as well, or the next class as well. So you'll get to see some of that as well. Now, when anything is at equilibrium, just like with, for any of you who understand a little bit about physics, anything that's currently sitting on the table in front of you or sitting on the floor around you is essentially at equilibrium with that location. If you go and put your hand on it and attempt to push it, what you're doing is basically applying a force and causing the equilibrium to shift. So you're causing, essentially in that case, the center of gravity, so to speak, to shift. And so you would be moving it. Same thing holds true in reactions. If a reaction is at equilibrium is going to be changing just a little bit. It's going to shift in one direction slightly, and then it'll shift back in the other direction slightly and back and forth. But if you apply some sort of force or some sort of stress to the reaction, you're going to get it to shift one direction and kind of stay in that direction, or at least create a lot of the product or the reaction that you're pushing it to shift to. And this is supported by what we call Le Chatelier's principle. I don't speak French. That's as good as it's going to get. Sorry. If for those of you that are country, it means Le Chatelier's principle, but same idea. And what that's basically saying is that if a system or a chemical reaction is at equilibrium and we subject it to a stress, it's going to shift in a way to relieve that stress. That's the same thing as if you're pushing something across that table. When you go to push on something and you're shifting its equilibrium, it's not going to move back towards you. It's going to move away. It's going to attempt to relieve the stress that you're applying upon it. And so the same thing is going to be hold true for a reaction. If I apply stress to the reactants, it's going to shift to the products. If I apply stress to the products, it's going to shift back to the reactants. Some ways we can shift equilibrium of a reaction are the same ways we can increase and decrease the reaction rate of a reaction itself. We change the temperature, we can increase or decrease concentration, we can increase or decrease surface area, and those things would shift it in one direction or the other. We are ultimately going to lead to an increase or decrease in the rate of the forward or the reverse reaction. Okay? So increasing temperature, concentration, surface area, increases reaction rate. Well, if I'm looking at a reaction and I have A plus B makes A B, and you're told that there is also a reverse reaction of AB breaking down into A and B, and you say, oh, well, if I apply a stress to the products, it shifts to the reactants. Well, that would make you feel weird because you might think, oh, well, does that mean it's decreasing the reaction rate? No, it's still increasing reaction rate. It's still doing all that stuff that you guys did your labs on, but it's just increasing the reaction rate of this reaction, heading from the products to the reactants versus the previous reaction. So shifting that reaction in whichever direction relieves the stress is what's going to happen as you apply that force. So here's an example, since that's a little bit verbal and we want to make sure that we can visualize it. So in this particular situation, you're told that this is an endothermic reaction, you're told that it has a KEQ of less than 1, and I will tell you, of course, that based on what you just took in your notes, that means that this reaction is naturally shifting towards the reactants. Okay, so that means that we're not creating a ton of product here. Now, in order to do that, and that may be a multitude of reasons. It may be that the activation energy isn't quite where it should be, or it's just the moles are not quite aligned where they need to be, the ratio's off, or whatever. But the general idea here, of course, is that by applying some sort of stress, I can shift that equilibrium. We see this arrow in the middle indicating to us that we have a reaction at equilibrium. And then we see these two up here showing a change here. So in this reaction, what we're looking at is basically saying that if I apply heat to the reactants, since this is an endothermic reaction, that means that applying heat will get the reaction to move forward faster. And so what that'll do is by applying heat, knowing that it's endothermic and the heat is going to go into the reactants, it's going to lead me to get more of the products. Okay, so since it's endothermic, the heat present on the reactant side is kind of shows us that, and that's this heat over here. Applying heat would increase that rate of that forward reaction and shift to the product side. So we're still doing exactly what we have been doing. We're talking about increases in concentration, surface area, temperature, etc. And we're talking about, but now we're looking at, okay, by doing that, are we shifting it more towards the reactants or are we shifting it more towards the product? In this reaction that we're looking at now, this is going to be a concentration example. KEQ is greater than 1, so what that means is that the reaction favors the products. So naturally, sulfur dioxide and oxygen gas are going to be naturally combining into sulfur trioxide more frequently. Now, if I were to add sulfur trioxide to that, what's going to happen is that, and that kind of makes sense, if you think about the fact that these are going to react because of concentration, right? Just like in biology, you have salt on the outside of something and less salt on the inside, so the water's going to move to the outside to try to equilibrate it, okay? And the same thing holds here in these chemical reactions. By adding some of this product over here, what it's going to do is basically say, okay, we're getting a lot of product here. The concentration is going up of the product, so let's stop that reaction. Okay, let's actually move the opposite direction. Not only are we going to slow down sulfur dioxide and oxygen combining into the other side, but we're going to show that the sulfur trioxide is actually going to break down into the reactants until it gets to an equilibrium. Okay, once it reaches equilibrium, then that means that this system shift would stop, and we would have back to the original case, which is going back and forth in a natural state. Okay, so I recognize some of this may be a little bit complex, but it's definitely within your realm of understanding. And make sure you're applying it back to reaction rate, and understand how you're seeing that the reaction can shift in either direction as a result of applying one of those stressors that we've been talking about all along. Okay, I'll see you guys in class next time.